This type of detector was constructed here, in Dubna, in the Neutron laboratory, by Nadachin and Luschikov. It consists of a polyethylene neutron moderator. Here you can see a barrel in which counters with helium-3 are placed. A neutron that moves into this zone slows down to a thermal speed due to the fact that it collides with a hydrogen atom. Helium-3 has a thermal neutron capture cross-section of 10,000 barn. Therefore, the process is as follows. A neutron reaches this point, it is slowed down, and is captured by helium. After this, the counter receives a signal. The sample is placed in the middle, and the process takes place inside. This means that there are 60 helium-3 counters, and the slowing down time of the neutron is 2 to 5 microseconds. The neutron lifetime, before it is captured, is 20 microseconds. After 20 microseconds, it has already been captured. The detection efficiency of one neutron is 60%. 550 grams of metallic osmium was placed inside. This amount was determined as a compromise between how much we wanted and what can be done legally. To export 550 grams of osmium abroad, you need to prove over a very long period of time that you wish to export it not as a noble metal, but in order to obtain super heavy elements. Despite all of the regulations, we were still able to carry out the experiment. So, how does this process work? It starts with a neutron flash. The first particle to come to a stop quickly was some kind of neutron, which was immediately captured and resulted in an impulse. This was followed by the second, third, and fourth neutron captures. That is, these impulses that arise from the flash are scattered statistically, creating this comb-like graph. In this picture, 4 neutrons from this burst were captured. Maybe there were 6 of these neutrons, but only 4 of them were caught and created this comb-like graph. Thereafter, it is necessary to minimize the background noise, and for this purpose, we took advantage of the Fréjus underground laboratory under the Fréjus Peak in the Savoy Alps, which are high, dense, and in which there is an automobile tunnel that connects France with Italy. The length of the tunnel is 13 kilometers, and in the middle of the tunnel, the height corresponds to 4,000 meters of water equivalent. The French underground laboratory kindly invited us to work in collaboration with them. The Modane laboratory is protected from cosmic rays, especially from muons, which have a great penetrating power. As a result, there is a very low background noise here, and in this low background noise is this counter, inside of which is the osmium. I'll very quickly show that, in principle, one could see a decay, even if it happened once a year. Considering the sensitivity of this experiment, half a kilogram of osmium containing an unspecified amount of super heavy elements, which can divide spontaneously, can be indexed at this sensitivity level once a year. This is the entrance to the tunnel. These are the helium-3 counters. 1 decay per year will correspond to a content equal to 7 times 10 to the power of minus 16 grams of element 108 in 1 gram of osmium. This is the level of sensitivity. And if we also take into account that element 108 itself is rare, with 10 to the power of minus 8 grams per gram, then we are looking for a certain super heavy nucleus in a sample of Earth at a level of 10 to the power of minus 23 grams per gram, which is 17 orders of magnitude lower than when looking for uranium or gold in the Earth. This is at the ultimate sensitivity level. And generally speaking, in comparison with all previous attempts to study superheavy elements, it is 9 orders of magnitude more sensitive due to the fact that osmium and hassium exist together. When we began to look at the background noise in more detail, we wanted to identify double coincidences. The probability of double coincidences, according to calculations, should have been 0.1 events per year. In fact, 36 events were observed per year. This means that the electronics bugged out. Factors came into play that were somehow unaccounted for, so we disregarded the double events and only observed triple events and higher. There were several triple events and higher. Over a period of 600 days, multiple triple events were recorded by the counters. The first in June 2005, then in February 2006, and another in December 2006. Therefore, the results were extremely low, and something had to be changed. Perhaps to try to increase the number of events by using a larger quantity of osmium, 5 kilograms instead of 500 grams, which is 10 times greater. But we understand that this is unlikely. Generally speaking, it makes sense to do such experiments in extremely low backgrounds and with high sensitivity. Nevertheless, if we now take these three events and consider this as the upper limit, I would like to point out that plutonium-244, which was found in the ground, is nearly as abundant as uranium-238, and it looks like this on the graph. And hassium will be located right here, if it has a half-life of 500,000 years. If its half-life is less than that, this point will move higher up on the graph. This is a depiction of our solar system. Now let's look at the calculations that were made. This is how the periods of alpha decay, indicated on the graph in red, behave, and this is how the periods of spontaneous division, highlighted in green, behave. Superheavy elements are somewhere above. They could not find it due to the fact that the Earth is considered to be very old, around 4.5 billion years. During this time, if superheavy elements were formed, it has already decayed, but it is still possible to search for it in space.